All right, welcome everyone. This is the August monthly meeting, and so we've got one paper, and then a guest talk for today. So just move my little menu. All right. So the first paper for this month is titled "Stealing Part of a Production Language Model." So it's always, for me, I always find it interesting how people try to game systems and do things like that, whatnot. And so this is a paper that came out, I think, a few months ago, I think in like March or April. So it's been out, but I thought I'd talk about it. So to understand this paper, you need to know a little bit of linear algebra. I'm happy to fill in some of the details. And then I think it's a really good way to reinforce if you understand the architecture of LLMs, because if you're understanding like what you're stealing and why that technique works, then that shows that you really, understand sort of the architecture and the data flow. So this is a paper primarily from people at DeepMind. And so the high-level overview is that most of the LLMs that we know today, like ChatGPT, they're decoder-only models. And of course, all of these ML models, they only work on numeric data. So your text is tokenized, and the tokens are turned into dense vectors of floating point numbers. These vectors get processed by the different layers in the model. And then ultimately what happens is these vectors get projected back into the vocabulary dimension with an output projection matrix. And then the softmax, scales those into things that look like probabilities between 0 and 1. So what they developed was a set of different techniques which can extract the hidden model dimension and the projection matrix, that very last linear layer in the LLM. They're able to do this without any access to the model itself. So this is a black box attack, and they actually successfully ran it against several OpenAI models that were completely proprietary and not available to the authors. So we'll go into the details, but basically the tokens, the techniques that they used are all going to use the probabilities that come out of the model, so that information, and this feature, which we'll discuss, which is called the logit bias, where you can actually turn up or turn down the probability of certain tokens. And then at the end of this paper, they have a section where they talk about different mitigation strategies. So just to kind of set the scene, we're talking about transformer models. And so this is the transformer from the original Attention is All You Need paper. And in a decoder-only model, we don't have the encoder, we don't have the left half, and then we don't have the cross-attention piece because there's no output from the left half. So if we redraw this straight through, then basically this is your decoder-only attention. And this blue box at the top, this linear layer, that's where in this paper they extracted the size and the weights. If this diagram doesn't do it for you, then you can also think of this in terms of the full LLM has multiple token positions, and it has multiple layers. There's still this one blue box at the top. And so this blue box at the top is, sorry if I'm covering that, but that's the output projection matrix. So for every token position, all of the weights are identical. The purpose of showing the multiple columns is just, to ease intuition in terms of how the LLM works. So how do they do this? We're going to start with an attack that is much easier to understand, and it's the fundamental math behind everything that they did here. But this specific attack is not very realistic for a real-world situation, but it gets us all the underlying information. So what we assume here is that you have access to all of the logits for this particular LLM. Okay, this is the assumption that's not realistic. So if your vocabulary size is 40,000, it means that you have all 40,000 floating point numbers before they ran the softmax, and you have them to full floating point precision. Okay, so what are we talking about? So for a model that has a vocabulary size, we'll call it V, and a hidden model dimension that we'll call D. Typically, the model dimension is much less than the vocabulary. So the vocabulary is going to be in the tens of thousands. 30,000 is relatively modest. 80,000 would be kind of a big vocabulary. And model dimensions are usually more like, earlier ones in the single thousands, more recent ones maybe pushing it to like 12,000, 16,000 or whatever. Okay. And so this output projection matrix, that blue box, is a V by D matrix. And so this is where the linear algebra comes in. And so because D is smaller than V, this means that this matrix can be at most rank D. Okay. So if you multiply various vectors by this matrix, then even though they may be V-dimensional, they'll have V different floating point numbers. The fact is they will all lie within a D-dimensional subspace of that. So the extreme example is if we just had a matrix where every single column was some multiple of the first column. So you have 1, 2, 3, and then you have 2, 4, 6, 3, 6, 9, whatever. Then in that case, you can come up with gazillions of different vectors. You multiply them by that matrix, all of the outputs will lie on a single line. All of the outputs are going to be a linear combination of the columns, but all the columns themselves are multiples of the first column. So that would be a rank 1 matrix. And if you have a rank 1 matrix, then even though you can have massive variety, high dimensionality of the vectors you multiply them by, you're going to wind up with all the points on a single line. So this is the same idea here, except instead of one-dimensional, it's D-dimensional. So the idea is that we can prompt our LLM a number of times, and each time we're going to get the full logit prediction. So I said, we're assuming that for every vocabulary word, we're able to get the exact logits, okay? And so if we take each one of these sets of predictions and we stick it in a matrix as a column, then we do this n times, okay? Eventually we'll get a fairly large matrix that's n wide, and it's each of those is going to be vocabulary tall, okay? So this V by n logit matrix that we build by doing lots of predictions, it looks really big. V's bigger than D, N's bigger than D. But the underlying math is that any output from the transformer layers that you multiply this by, if everything is coming from this projection matrix, it can be at most rank D. So everything's going to lie in a D-dimensional subspace. How do you practically go and find out about the rank of a matrix? So we can use singular value decomposition. So if you don't remember that, that's fine. But you get two triangular matrices, and you get a diagonal matrix in the middle that has the singular values akin to the eigenvalues. And so if we look at that middle matrix, the singular values, we can plot these. And what'll happen is there'll be some bigger ones, there'll be smaller ones. If we had perfect precision, then we would find that we only have D singular values. So looking at this next chart, you can see, so they ran this on, which was this, Pythia 1.4 billion. Pythia is an open model, so we actually know what the ground truth answer is, okay? It's supposed to be 2048. If you do 1,000 different, they call them queries, but you do 1,000 different inputs to Pythia, and you arrange all the logits, well, you can only get 1,000 singular values, you'd only get rank 1000 out of it. What if you do some more? So then they did 1500 and you get the orange line and it shows more. Okay. What if you do 2048? Then you get this green line. Okay. And then if you go past 2048, then you see this different phenomenon. Okay. Where it doesn't, if you go to 2500, the curve doesn't go all the way to 2500. What happens is it sort of stops at 2048. But then eventually you get these really, really small magnitude singular values at the end. And the reason for that is because of floating point rounding. So when you say that this column is a multiple of that column, might not actually be an exact multiple because one of the values might be off in like the 8th, 10th, 12th decimal place or something like that. And so you'll get these other phenomenon that look like are in addition to, you know, the main phenomenon. But the good news for this attack is that because they're only going to be rounding errors in that last decimal place in the mantissa of the floating point number, it turns out they're going to be really small so that the singular values you get are really small. And so that's where you can see that basically, if you take all the singular values and you sort them in size, that you start out with big ones and then eventually you get to smaller and smaller. And then that's where things just sort of hit a wall at the hidden dimension. And then eventually orders of magnitude smaller than the smallest real singular value, you get these floating point rounding type other things that show up later. So if you look at this chart, you can see like, okay, there's small ones, then there's the ones that are right here where the dotted line is, and there's this weird thing that keeps happening once we pass 2048. Every single time we get this weird phenomenon right here. And so you can say pretty much, I'm pretty sure that this model, the hidden dimension, the residual stream size is 2048. Another way that you can do this that's sort of less hand wavy, where I'm saying like, oh, the curves look really funny at 2048, is you sort all the singular values and you take a look at the ratio between a singular value and the next smallest one. And so what's going to happen in this region, the singular values are all going to be close to each other and the ratios can be close to 1.1, whatever. It's going to be relatively small. And then somewhere here, you're going to go from the smallest real singular value to the biggest floating point rounding error fake singular value. And it's going to be a very large number. And so if you plot that, you get a curve like this, where you say, oh, I have these ratios. And then bam, there's this huge spike when we go from the smallest real one to the biggest fake one. And then the fake ones are all similar magnitude. So then whatever. So this is a log scale on the y-axis. But otherwise, what I'm talking about in terms of like the ratio is all going to be pretty similar for these singular values. So let me pause here because this is not the actual attack they use, because again, it's unrealistic that you get the full set of logits for every single vocabulary word. But this is the math that ultimately they're going to convert everything to this problem in terms of how they do it. So any questions about the basic idea here in terms of like we can actually use this attack in order to get at the size of the output projection matrix?
So this might not have been explored in the paper, but if you had the layer right before was even smaller, could that theoretically constrain the next layer and then you get fooled because that's a lower rank because of previous?
Yeah, so I don't know if online you could hear. The question is, what if somewhere before the last layer, the model was even smaller? Then yes, you would actually get that smaller number. And in fact, they found that GPT-2, I don't remember what the number was, but it was like 768 was the hidden dimension, but they actually came up with 757 because, and so then they're like, well, that's weird. Like, everything else, we either got it exactly right or we're only off by 1, right? But this one, we're off by 11. Yeah. So then they actually did analysis of the model itself, and they found that for whatever reason, the transformers, all that, was only 757 dimensional. So that is exactly what you're saying, that it was constrained before it got to the output layer. All right, whoops. So that's all well and good to say, oh, I know what the hidden model dimension is, but that's not too much of an extraction. That's not really stealing too much. Turns out there's some math, there's a proof in the paper, okay? But that if you do this very attack and you do the singular value decomposition, we were talking about the singular values. So in the singular value, you have this U times sigma times V is how you decompose the matrix, okay? We were talking about just the sigma matrix. It turns out that the U matrix is in fact the full vocabulary output projection matrix. Now, technically speaking, it's not necessarily going to be the exact values that are stored in the model, because it could be a permutation of it. It could be a sort of a rotation of it. And in their primary attacks, it could even be just a linear and affine transformation of it. So like every number could be double what the ones are in the actual output matrix, or it could be double -3, okay, a linear transformation. But for all intents and purposes, if for some reason it was of value for you to understand the embeddings and the output projection, you would be able to extract something that's as useful, even if it's not necessarily the exact copy that they have. Because again, in terms of output probabilities, it doesn't really matter if you just like, you know, if you have like double of everything, you're still going to get the same you know, the word that is the highest probability is still going to be the highest probability, even if you add one, or even if you double all the probabilities. So I don't think I have this in the slides necessarily, but they do say that, like, hey, we're not saying that this would in fact actually be all that terribly useful to somebody. I think that was part of their ability to publish this, because if this was like actually hyper useful for like stealing somebody's LLM, they would have had to be a little bit more careful. So in the case of the results we see for OpenAI, they actually contacted OpenAI and they got permission to publish the results. So for a couple of the models, they withheld some of the numbers, but for others, OpenAI said, yeah, for this Babbage model, we're actually about to deprecate that because we're coming out with a new GPT, 4.0, blah, blah, blah. So no biggie if you publish those findings, because that's actually an older, weaker model that we don't really care if people learn things about. Yeah. So we've only so far talked about if you had the logit for every single token. What we're now going to get into is some more realistic scenarios. I don't know off the top of my head exactly which features different providers offer. Okay, so let's talk about more realistic. So first of all, real APIs only offer you the top K probabilities. They're not going to give you 30,000, 80,000, whatever of them. And so it's pretty easy. So then the other thing that they offer is this thing called the logit bias. Okay, so the logit bias allows you to add a value of your choosing to the logit for a particular token prior to it going through the softmax. Okay, so if you add a large negative number, what you're doing is you're downweighting the possibility of that coming out. If you add a positive value, then you're increasing the probability. So for example, if you were generating a story about farm animals and for some reason you said, I do not want any cows in my story. Okay, I'm okay with chickens, I'm okay with whatever, but I don't want any cows. If you used this logit bias and you said add -100 to the token cow, then for all intents and purposes, you're never going to see cow in this story. Now, that there may be more work that you need to do in order, because maybe cow comes in a different way. You have to make sure it doesn't say the word bull, or if cows with an S is a token, and whatever. Like, so there may be other synonyms and other things you need to do, but this is the kind of thing that people do with these logit, with the logit bias functionality. All right. And so basically, what you can do is you can say, I'm going to pick 5. So if top K, if they only offered you the top 5 logits, if you just add a huge number to 5 different tokens, then you basically now have the probabilities for those 5. And you could just cycle through doing 5 at a time. And so if the vocabulary is 50,000, it would take you 10,000 runs through the LLM. But then after that, you would have all 50,000 logits. So that's like the next more complex thing. It turns out that in fact, you don't actually get the logits. What you get are the probabilities after the softmax. So there's a slight further complication there. If you look at this formula down here, this shows you what is the log probability that you actually get from the API. And so if you add B for one token number I, then for all the other ones, you're just going to get e to the whatever the LLM says. And then for this one token, you get e to the whatever it says plus b, okay? It turns out, though, that if you do this for 2 different tokens and you subtract, you get the difference between the 2 of them, then this term here on the right cancels out, because this term appears exactly the same for every token. If you have a reference token, and I apologize if my Zoom menu is, I tried to move this, but if it's covering up that formula at the bottom, if you subtract the outputs for 2 different tokens, then this right-hand part cancels out, and you recover the original difference between the 2. So an easy choice is you pick the actual most likely token as your reference, and then if they give you the top 5, then basically you can do that plus 4 other ones, and 4 at a time. So if your vocabulary size is 50,000, then it would take you like 12,500 or, well, 12,200, whatever the math is, generations of the LLM, but then 4 at a time, you can get all of the other ones relative to your reference token, and you can do our basic attack. You build that matrix using all of those probabilities, and then eventually you do the singular value decomposition and get the full matrix. All right, you guys with me so far? All right. So now let's get a little bit more complex. Question? Okay, cool. Sorry, so this Hiro is saying, so if you have the top 5 log probs and the logit bias, you do 4 at a time and you cover everything. In the paper, they go into a little more detail of different variations of the algorithms that all work fundamentally the same, but they become more efficient in the number of LLM queries that you need to do in order to extract things. So if you think about it, like we're extracting 4 at a time, whatever, there's like other information. And so if you like built a system of equations, you might be able to then more quickly hone in on things rather than just doing it 4 at a time. It turns out that you would think that if you need to do this reference business, then you need at minimum top 2 so that you have the reference one and you have another one. And clever them, they came up a way where if they only gave you the top 1, you couldn't do the subtraction in a single LLM pass. But what you can do is you can do one LLM pass with a bias of 0 and another LLM pass with a bias of -1. And if you do those 2, you compare the results, you now have effectively done a kind of reference thing. And so then basically you would end up having to do every token twice, but you more or less can eventually work your way and into doing sort of the same thing and getting the whole okay. All right. So then I believe we have one more slide, one more level. So finally, you can do this attack with the logit bias feature and no probabilities whatsoever. So basically what you need to do is you need to see where if you change the bias, if you increase it, at some point, does this other token become the most likely token? It becomes the number one token, okay? So you set your temperature to 0, so it's always outputting whatever token is the most likely. And then if you want to know what the probability of the word dog is, you just, add 1 to it, add 2 to it, add 10, add 100. And at some point, you're going to add enough that it becomes the most probable token. And so what they say is that you can just do a binary search. And using a binary search, you can quickly hone in on what's the minimum value that I need to add to dog in order to get it to be the most probable token. And if you do that, then once again, you know the difference in the values between the most likely token, the reference token, and the word dog. And so you can do the math and you can figure out that basically it's like log base 2 if you're doing a binary search. So then there's other algorithms in the appendix, again, where you can have a more complex algorithm that does multiple tokens. But ultimately, they're all fundamentally doing this same technique where they're saying, I need to figure out what are the outputs from this layer, and I'm going to do this singular value decomposition, and I'm going to get both the rank and the actual values. So here's a table showing, I can just sort of move this. Let me try the time. Here's a table showing a couple of these different attacks that they did. And some of these are from the appendix, the ones that begin with letters, the ones from section 5 are from the main paper. And you can see, for example, like this first row is a pretty reasonable attack where you only need the top 5 log probabilities for any given LLL inference pass. And they were able to get 23 bits of precision. So that's like 8 million, right? And it only cost them 1 query for every 4 vocabulary words. So if it was 40,000 vocabulary words, it only took them 10 queries to get each of the values to within 1/8 millionth in precision. And you can see here's these other ones. So here's some actual results. So these are some of the older models, the Ada, Babbage, and Babbage 2 models. They also ran it on GPT 3.5, GPT 3.5 Turbo, and basically they got the results. They emailed OpenAI. OpenAI said, all right, guys, yeah, that's right, but please don't publish that. So they have asterisks here where they don't show the number, but they said that OpenAI did give them permission to run their attack. They gave them permission to publish the older models. And so, they put a thank you in the paper saying, thank you for letting us doing this. And in consideration, we won't publish the ones that you don't want us to. But so at the cost of these models, you can see that they were able to fully extract the information for Babbage for $2. So it's not like this broke the bank for somebody to be able to do this. Okay. That's extracting just that it was 2048. To get the full weight matrix, well, they had to go from $2 to $12. Woo. And the only reason why this number is bigger is because this technique, if you do it once, you can actually have floating point rounding errors that add up that cause you to get like not quite good results. So you want to actually, instead of just extracting the word dog once, you might end up extracting the word dog 3 times. And then from that, you can kind of average out, you can get a solid number. And so then they show that basically all of their weights were within 7 times 10 to the minus 4 of what the actual weights were. So what they did was they got the real weights from OpenAI, OpenAI shared them with them. And so then they just figured out what the linear translation was between them. So they translated theirs so that they're exactly the same as the OpenAI ones. And they said, what's the root mean square difference between our weights and their weights? And this is a ginormous matrix, right? This is what, again, like 30,000 by 2048, and there were, RMS error of 7 times 10 to the minus 4. And so if you look at the notes, they actually did not run their full attack on GPT-3.5 Turbo, because even if they deleted it, once you do something, data on the internet lives forever, right? So they actually say they didn't even run the experiment. But they estimate that it would have cost whatever, $2,000, $8,000. So really not huge. All right, so then they end the paper by saying, well, what are some strategies if you're actually a vendor, if you're OpenAI or you're Google or you're whoever, and you don't want people to do this, okay? So to completely prevent the attacks in this paper, one thing you could do is not provide the logit bias feature at all. Apparently, some people want this. I haven't used it before, but apparently some people want it. So that one's not necessarily too practical. One thing you could do is you say, well, instead of giving you logit bias, I will just give you like a blacklist. And so you could just say, like, don't ever output cow. And so then basically, I imagine what you would do is you would run the model in full, and instead of adding some number to cow, basically what you would do is you would remove it from the outputs being considered. You would just mask it off. And if you do that, then for the person who, like in my example, wants the story, and they don't want the story to have cows, you've given them that functionality, but you're not actually disclosing any information about the word cow. They talk about some other things you could do. You could change the architecture of the model. So they said if you had 2 linear layers with a higher dimensionality in the middle, that would break this attack, but that would be extremely costly because you already have a 40,000 by 2,000 matrix for output. If you actually turn this into something where you project it even higher than 40,000, so then you have a 40,000 by 80,000 and an 80,000 by 2,000 matrix, that would just be like very expensive. And then another technique they came up with is what they call post hoc alteration. So you train your model completely like normal, you don't change the architecture, but after the model's frozen, you say, now I've got my predictions and I'm just going to run them through some miniature network that changes the dimensionality, that does various things to it or whatever. And so I'm adding a bunch of orthogonal noise, which it's cheap because it's not really part of the model, it's just post hoc. But to the end users, they might not be able to tell the difference.
There's a question about the if you're doing this on an embedding model versus a chat model, will that function the same? So,
yeah, so my understanding is it does not matter if the model is a chat tune model or not. That does not, the weights get changed, but the architecture of the model remains unchanged. So it still has, as in the diagram that I showed, this one linear layer at the end that does the output projection. So that's a good question.
you go back one or
Yeah.
2 slides.
If my computer will let me.
Yeah. So on that though, so those top 3 models, those are all embedding models, and then the bottom 2 are actually the chat instruct tune
Oh,
models.
gotcha.
So I'm kind of interested in those don't have vocabulary necessarily, because it's just outputting embeddings, correct? And so that probably doesn't have the logit bias feature, because that wouldn't really make sense on.
I'm not that familiar with Ada and Babbage. I thought that their embedding models were like BERT-like models as opposed to GPT-3-like models.
Yeah, so the architecture though, in my understanding, is going to just output like 1024 or whatever, and it's just a vector. So you don't have a vocabulary that you're querying against necessarily, I don't think. So I'm not sure exactly how that would differ on that. Because I don't think they give you the logit bias thing because you don't have any vocabulary to even push back against.
Right, yeah, correct. You enter a token and you get a vector. Yeah.
So
It's a good question. Ultimately, if you have a BERT model, it is trained on mass token prediction.
yeah,
So it would have an output vocabulary and an output projection matrix. Normally, you don't care about that if you're just using the classification or embedding. But if they do expose all of the outputs for every token position and not just the classification token position, then you would be able to use this stack, and you'd actually be able to do it pretty fast because you'd be able to extract from all your tokens. Yeah. I don't know if you can just check real quick, but
I'm looking.
yeah.
Curious what that is.
But yeah, I think you'd have to use a position other than the classification token, to your point. Yeah.
So we got this logic bias stuff earlier.
Yeah, I think it, even though just stealing the last layer is not necessarily that dangerous to an OpenAI or whatever, I think they just don't want that out in the wild. They want to encourage people. I don't know. Earlier this year, someone was talking to me about the whatever the broken windows. I don't know what you call it, philosophy or whatever. But so like, if there were publicity that somebody extracted the output layer, maybe that would encourage more people to try to attack their model. So they thought it would be better to just like not. I don't know. I'm just guessing.
There's a whole
Yep.
I thought it was it's like, I imagine that with the snake, like, it kind of look like a dog or something like that. Like, the snake is classified as a dog or something.
Yep.
But now it really gives like kind of legitimacy, like, you know, this is kind of the last 4 years.
Yep.
Yeah.
Yep. Yeah. And I have just like one note from the authors on my last slide. So one more slide here. So this is prevention. So this does not. I'm sorry. So I covered this one. This is how you could completely prevent the attack. Then the other thing you can do is they have mitigation. So these are techniques you could use that make it more expensive or less accurate for somebody, but you're not completely preventing them from doing these. Okay. So one thing is you can provide logit bias and you can provide log probs, but just don't allow those features to be used simultaneously. So if you do this, then there is that attack that they described where using just logit bias, you can do a binary search, but it's still a lot more expensive. Okay, so whatever the cost of the other one is, it's like log base 2 of whatever precision you want times more expensive. So, you know, log base 2 of 8 million is whatever, 23 times more expensive. So even if that other one was whatever we said, $2,000, you know, now you're up to $50,000. You could add some noise to the outputs to make them harder to interpret, but adding noise potentially makes your LLM less useful for your legitimate users, and you might not want to do that. Maybe you somehow limit the number of logit bias queries for each prompt, but that's kind of crazy. You have to save state to keep track of how many times each prompt was used. And assuming that the adversary is clever enough to use different logins, then you have to keep this state across different users. And then like there's privacy issues of trying to keep state across users and blah, blah, blah. So probably not very practical. And then maybe you somehow build some sort of AI that can detect whether or not some behavior looks suspicious. And currently nobody seems to be able to do that. The black hats are definitely way ahead of the white hats in terms of figuring out how to do an attack, but also how to disguise their attack so that it's not so obvious. And so I think you were saying that the logit bias feature went away, and so that probably was the simple path. All right, so to conclude this paper, they developed a range of techniques. They're able to extract the final layer. This is completely black box where they have no access to the model itself. And what they do say is that this technique does not currently seem extensible beyond the final layer. Okay, the transformer layers are highly nonlinear, and so this linear algebra is not going to let you attack something that highly nonlinear. And they also say that finding out the final layer doesn't seem to be that practically useful. But they do want to point out that architectural decisions and seemingly innocuous features such as logit bias, top K log probs, do impact the security. So when people are designing things, they should actually be thinking about that. And so ultimately, they're not saying that this particular attack itself is going to change the world. It's not going to change anything, but it does kind of point to where something you might have thought was really small, like offering log probs, maybe you do need to think harder about like what implications that has. So yeah, so I just wanted to kind of like tag like that comment in terms of, at first for like images, the adversarial attacks were all white box, where it's like, oh, I'm gonna like, run back prop, against this, and I'll turn the whatever that, the panda to, whatever, yeah. But since then, we've seen techniques that do not require that word black box, and they're not. They're a little more obvious if you bother to take the time and inspect them. The images do look different. They do look suspicious, but they still work even with no access whatsoever to the weight or the architecture. So yeah, it is an interesting field, and if it costs you how many hundreds of millions of dollars to train the model, you really don't want somebody to be able to steal your model. So I'm sure a lot of people are sort of trying to stay tuned on what's happening in this area. Any other new questions? Or nope. All right. Any final questions? All right.
I have one. So extracting out the final linear layer is interesting, but not that useful. I've seen other attacks that are basically like, let's lift their entire model by just sending a whole ton of queries in and saying, we know what the input is, we know what the output is. Now just train something in between that mimics that mapping from input to output. So there's a ton of costs associated with just getting that, like you have to pay for all of the API calls, so it all tracks up. So like a commercial attack on this would be funny, where you could basically say, like, I'm going to just feed OpenAI's model to everyone else at some small loss. So they charge a certain amount, I charge a certain amount minus a little bit, and I attract people to just basically be a front end to that. And all of their queries, I only charge 10% less, and that's the amount that I eat in order to generate a whole bunch of training data to mimic this model. And then you're only paying a small premium on, so that's my evil idea, is take an OpenAI clone and then charge a little bit less to get the users, and then soak up the model in the meantime.
Wow, that's pretty interesting, man in the middle attack. Yeah, so online, if you weren't able to hear what Ryan was saying, basically he's saying, advertise broadly that Ryan LLM is just as good as GPT-4o because it is GPT-4o, but charge whatever 5% less than OpenAI. And so then a bajillion users use your thing and they're like, yeah, these results are just as good as OpenAI. But meanwhile, you're saving off a copy of all their results so that you can basically later on, I'm thinking distilling the behavior of that big model into a smaller model, which probably you won't then be able to get 100%, but you can get a smaller model. And at way, way less than the hundreds of millions they spent training GPT-4o, you could get something where you could now truly offer cheaper inference. 98% of the performance, truly half the cost of inference, and you never had to spend hundreds of millions. All right. So when you need to hack into some company, you know who from this meetup you should hit up first. All right. Any other questions or comments?
George has one.
Yeah, I can try and
I can read it. I can read it from the chapter. He's asking if anyone's aware of a paper that uses techniques to recover part of the training data that the model was trained on. Seems like it would be doable for open source model.
All right, can you recover part of the data that the model's trained on? So there's a lot of research. I have not followed all of it. So Ryan was talking about a sort of distillation behavior type attack, which is very different from trying to extract like raw, actual, floating point values of the weights. And then there's also things talking about the data. In particular, you worry about edge cases. So like when you're reporting statistics, like say the census is reporting, health data for different counties in the US. Well, in that county where the population is 200, if you're the only male over 80 years old and they have a bucket that says what is the average income, the average whatever for males over 80 in that county, they basically now, accidentally exposed your data, right? So for that type of thing, there's some standard things where you say there has to be a minimum number of people before you report an average, right? So there's similar things with an LLM where can you extract? I've seen stuff, but I'm afraid I can't really answer the question that well. I'm not totally on top of all things, but it would be particularly problematic. It in general would be problematic if you exposed any of your training data, but it would be even more problematic if you were exposing like, whatever, somehow I had access to Elon Musk's tax returns and somebody was able to like extract that training data from it. That's much more interesting than just like, oh, look, one of the training pieces was this Wikipedia page. So sorry, George, I don't really have any more specifics.
I'm sending.
No, that was great. Thank you.
All right, so you're putting stuff in the chat?
Yeah, there's a bunch of papers that I just.
Yeah, cool. All right. Yeah, so Liam, if you're good, we can take whatever 10, 15 minutes if you want to share a little bit about some of the things in your ML journey, some of the top things.
It's such a night and day.
No, it's
listen, okay, show of hands, who's coming into ML from like engineering background in this room? So everyone is from like more like a data science sort of way, because okay. From data science background, okay. So this, I feel like my presentation is more like for engineers who need to understand what it is.
so, I mean, I don't want to like force you.
No,
Okay.
I'll do it.
But I would say, even if you want to just do like a 5-minute version, it doesn't have to be about like, oh, wow, I just taught something that all these people didn't know.
I'm happy to.
Okay.
Go ahead.
Let me
So-
see here. So
Yeah,
I
this
can
should be-
share your slides, but I don't know if the audio will be great. So it might be easier if I just flip my computer and have you drive. Use the slides that you sent me.
Yes.
All right. I have too many windows open. I think this is it.
Yeah.
Don't think you're muted, but you can double check.
Am I visible? Like, can people see?
Yeah, I think camera and microphone are still on.
Awesome. So this is basically going to be like the polar opposite of that. But this is like, I've noticed that, like, some people come to like a bunch of data meetups, and I think in the media a lot, we oftentimes get like, a we hear a lot about like LLMs and computer vision, and a lot of really like fancy algorithms do a lot of very complex tasks, whereas a lot of people just getting into ML should learn, say, like the key principles of what it takes to train and to train a model first. So that's basically like, this is the presentation that I wish that I had had when I first started out in machine learning. A little bit about where I started is like, I started off with a series on convolutional neural networks, right? And so I built this big Inception ResNet v4 algorithm when it turns out, I had no idea what to do with it. So this is just going to be like, a rundown of like the basic concepts. So, basically, the one thing that I want to start off by saying is that for a lot of cases, you should not start off with a neural network. In fact, you probably should never start off with a neural network unless you know that it is a task that specifically will require one. There's a lot of reasons for that. Like an anomaly detection, they get away with using naive Bayes, where a neural network would be maybe more accurate in some cases, but a naive Bayes is just a lot simpler and more explainable. And some of the reasons why you shouldn't start with a neural network is, complex, takes more time to develop. That leads to it being less maintainable. If a neural network breaks, then, it takes a larger degree of skill to diagnose what the cause of that is. It's also a whole lot less explainable, although, as Ted mentioned, there are ways that you can, hack it into being explainable, and a lot of work being done in this at the moment. Typically they are less explainable by a long, big margin. They're also like, more slow and more costly. Inference time is a lot larger. Like for instance, in fintech, right? A lot of times for high frequency trading, a neural network would be more accurate in determining opportunities, but those opportunities will be way out the door by the time it actually makes the prediction, right? And I would recommend that, like, if anyone doesn't know what the Turing's rule of least power is, to start there. It's basically a principle that you want to start with the least powerful mechanism first, whether that's, in coding, machine learning, even vendor tools, and it's a principle that, holds doubly relevant here. So literally, after that, I'm just going to go through basically linear regression and how it pertains to neural networks. This is basically arguably the simplest form of machine learning that exists. In fact, it was developed in around 1950s as a perceptron. At the time, people were like, okay, well, what can I even use this for? But it basically highlights the different fundamental principles that exist for the training of basically all machine learning models. So the model basically is just like, statistically speaking, how different variables relate to each other. It can be like, say, it's basically an equation at that point. In this case, yeah.
I am sorry to interrupt, but I think I stopped screen sharing.
Oh goodness.
Yeah, sorry. All right, that was my bad also.
Oh, good. Yeah, so like, the equation for a deep neural network is going to be really long and complicated. But for linear regression, it's just the simplest thing, you could think of. Y equals mx plus b. This is literally what a model is. So whenever someone says a model, that's all it is. In this case, it's a supervised model because we know what the output is. We have a label. And then this is a model with high bias. Bias just means that it's generalizing very, very well, and it has a low variance. A model with very high variance, you can imagine it just connecting those dots, whereas this has high bias, so it's making sweeping generalizations about the data. You could determine this algebraically. You wouldn't even need to train, a linear regression model. You could just determine it like this. But the reason people don't do this is because this is in cubic complexity time. So for every observation, you would cube that number of iterations. And so it's not really feasible to do. But if you're not aware, then that's the asterisk I'm going to put on all of this. M in this situation is usually considered the weight, and B is considered the bias here. So weights and biases. So when we want to judge what the goodness of fit, we want to figure out how do we determine this. And this is called the loss function. So if you see it in papers at all, the loss function is how we determine how good this thing fits. With one data point, it can be pretty much anything. But when we add more data points, we can start to see that this isn't a very good line. But we can't really explain why that's not a very good line. We could measure the distance between each of the points and the line, but if you can kind of imagine, that doesn't give us any significance as to why that third line is better than the second line. If you were to add up all those residuals, they would be exactly the same. So that's why we square that. We basically find the difference between, the squared residuals. This penalizes large residuals more, and mean squared error is used in lots of neural networks and lots of different machine learning algorithms. But the loss function is, that's basically all a loss function is. In this case, it's the sum of the square residuals divided by the total number of observations times 2. I'm going to get into why we times that by 2 in a second. It just makes it a little bit simpler. But and the model in this case is mx plus b. So that's just kind of a little bit of an elaboration. You see that if one of the data points is really far away, then the loss is going to be far greater if it's squared. So we do gradient descent by finding the partial derivative of each parameter, pretty much, because a gradient is just the partial derivative of each one of the input parameters, right? So if we wanted to say do that here, we'd take d. We're finding the partial derivative of m, mx plus b, the slope, essentially. So we'd want to find the partial derivative of the y minus that model, which is mx plus b squared, right? So you could do that in calculus using u substitution, where we just take y minus mx plus b as u in this case. So we, find in respect to m the derivative of u squared in that case, which is 2u times the derivative with respect to m of u, which is, d dm y minus mx plus b, which is negative x. Because if anyone doesn't remember this part of calculus, mx is the only term that actually has m in it. So negative x is the derivative. So that ends up being 2y minus mx plus b times negative x. That's the derivative, that's why we put the 2n on the bottom. You don't have to do that. It doesn't really make a difference, but it makes it nice and clean. So for each one of those samples, that's going to be the derivative with respect to m. So if we wanted to update m, and the reason that we find the derivative in the first place is we want to figure out which direction to update, And the learning rate is just a number that we multiply that by, so we're not like overshooting. You know, it's typically between, say, like 10 to -3, 10, -5. And in this case, that equation above is pretty much like what the optimizer is. So you see like an optimizer being used in particular circumstances. It's basically just the thing minimizing the loss function by updating model parameters. In this case, we're just descending the gradient, and we're using stochastic gradient descent. Stochastic just means in batches. So this is, row by row here. This isn't, a better way to think of stochastic gradient descent is with matrices. So there was a lot of, that's where, understanding matrices comes into, play, as well as trying to attack LLMs, definitely, like linear algebra and that kind of stuff. But very simply put, when we do multiple linear regression, we can just start to think of these as matrices. So for multiple linear regression for multiple features, right, the equation will look somewhat similar to, well, it'll just look like this. We're considering that n is the number of input features and that it has a different slope for each one of those, right? And there's one bias. So what we can do is we can actually rewrite this as just y equals bx, where x is, the batch, y is the batch of, outputs, and b is just all the coefficients. So it'll look kind of like this. We have one for bias and a bunch for, the different slopes. Now you can split that bias out towards the end, right? You don't actually have to have it in the same matrix, but for this, it'll be a simpler demonstration. Basically, like, we added 1 as a column in this, input matrix because basically the bottom is the same as applying the top equation to each one of the observations, right? B times 1 plus M0 times X00, etc. That's for each of the, elements in the input batch. It's just a lot faster for, computers to understand and calculate to do it this way. But in order to do gradient descent, you basically just do the same thing that we did earlier, except, this is the same exact equation. You're considering a particular batch. You're multiplying y minus bx, and bx is the model, by its transposition, which basically just, flips the rows and columns of a particular matrix. So if you can imagine multiplication, that's exactly the same thing as squaring it, is multiplying it by its transposition. So, if you reduce that out, this looks very, very similar. You just get the derivative, and you update it in the exact same way. Now, alpha here, that's the learning rate. If you see it in papers, that's basically what the learning rate is. So the update looks very, very, very similar because it's the same. Really quick, how this extends to logistic regression. This is when you, instead of predicting like a continuous numeric value, you want to predict something between 0 and 1. Then you put it within an activation function. In this case, we're going to consider sigmoid. Sigmoid is, 1 over 1 plus e to the negative x. It's commonly denoted with a lowercase sigma. For neural networks, of course, you'll see ReLU is a lot more common because it's easier to compute, less cost intensive. But basically all it does is it turns linear regression into, mx plus b within this sort of sigma function. And it looks something like this. Basically, instead of determining a line of best fit, you're determining a best split, between the values 0 and 1. And now you know how neural networks work. Why? Because that's literally just a neuron. Like logistic regression is literally just a neuron. In fact, if you have a neural network with 3 layers and 3 neurons per layer and, sigmoid activation function, it would just look like this. So as you can see, this is a model just like linear regression, basically like anything, and it can be put within the equation of the loss function and computed in the exact same way. In this case, we did actually take out the matrix for weight and separate it from matrix for bias. But again, you could do it either way. I don't know which one PyTorch does under the hood, but it's very, very similar. And you can compute the gradient from that using the chain rule. So if you hear back propagation or the chain rule, that's basically all it is, And so for each neuron, it's very, very common to see, circles, right, for each neuron that are connected to each other in all sorts of complex ways. But really, all that happens here is you just create three, in this case, there's 3 neurons per layer. You just, create 3 columns in that coefficient matrix or the learned parameter. And the bias, you do something similar. So that makes it very, very computationally effective to do. So with that in mind, all you really need to know to train basically, most machine learning models, if not all, is, you're going to need to know the model, which defines the variable relationships. In this case, it's linear regression, or it could be a deep convolutional neural net. Doesn't matter. The loss function, which describes how well it fits. In this case, it's mean squared error. It can, vary. You can do cross entropy loss. You can do a whole bunch of other stuff, or custom loss functions. It doesn't matter. As long as it's, all differentiable, it works. And then the optimizer, which minimizes the loss function. In this case, it's a stochastic gradient descent. If you see stuff like Atom, AdaBoost, it's basically variations of this, but with some extra parameters. Actually, like some of them have like decaying learning rates. They have some extra, bells and whistles as far as that goes. The optimal way to determine, that learning rate programmatically is actually by computing the second order derivative or the Hessian of the gradients to find out, how fast the thing is moving or how fast, how having trouble describing it. But it's just very, very computationally expensive to do that. So that never really happens in practice. But in this case, it's stochastic gradient descent. That's used for a lot of different algorithms, even very complex ones. And then the hyperparameters you choose, which are, in this case, learning rate and batch size. And I didn't really cover batch size. It really depends on the algorithm, but it's kind of self-explanatory. And then I didn't cover this either, but the evaluation metrics should be different than what the loss function is, because it's telling you how well the model is working, not, the model, how well it's working. Like for instance, in text to speech very recently, like, there are certain evaluation metrics that, compare the sequences of particular values. Like there's a lot of variation here, but the evaluation metrics you're going to see in every model training is probably going to have is going to have some variations of these fundamental pieces. So if you're just starting off in machine learning, just look for these things in pretty much all the papers you read or, all the content you consume. And happy hunting. Go to get some Kaggle stuff. Yeah. That's all I got.
Thank you for this briefing. I should have mentioned this earlier, but you have that survey you asked about the backgrounds.
Yeah.
I actually have both.
Oh, cool.
I got a bachelor's in chemical engineering and a master's in computer science.
Mm-hmm.
So I was kind of so I didn't want to raise my hand twice.
Fair enough.
Yeah.
Now I know that this is like, much more simple than the thing preceding it, but does anyone have any like, questions of just like these basic sort of like, aspects of machine learning?
Comment?
Yes.
I don't think they'll be able to hear me, but my last job, one of the things my company did, we did medical appointments. And so it was very important to us, basically this curve, which is how many people are gonna like schedule an appointment, like for each time we call them and remind them and ask them to schedule. and it was like different for different age groups and for whatever, but like, basically it was like, we did a linear regression and like, there were people who wanted to do like all sorts of fancy things and, you know, we had to do a slight tweak to make it nonlinear, but basically it's like, no, like, this is really gonna work much better if we just stick with something simple and, you know, people wanted to jump to like all these like fancy things. It's like, no, I think we should stick with linear regression.
Oh, yeah, for real. I mean, honestly, like I don't know, me personally, I feel like it's just so much more impressive to use like a simple model to do something complicated than the other way around, you know?
That's another case. It just shows that you actually know your subject and just rolling a neural net because.
Yeah.
It goes without saying that it's computationally absurdly expensive. It's the reason why it took 50 years for the IT industry to even start using it. I mean, we've had it ever since 47. That's how long it's been around, but
47, yeah.
yeah, but no, it's only 8 years ago that people were able to start using it.
Yeah,
That should show you just how much power it needed to use this.
yeah. And actually, I mean, deploying machine learning models, you know, neural networks are very, very big in storage costs as well. And imagine like if you parallelize that at scale, you know, that's gonna be a lot more money. And I don't know if anyone's mentioned this recently, but you know, LLMs can take, you know, I was reading a paper where they were bragging that it only took $30,000 to train a particular version of an LLM, which is actually kind of impressive. And that's the thing. It can be like hundreds of thousands of dollars to millions of dollars. You know, just try linear regression on. I'm just kidding. Don't don't for large language tasks. Probably not the best solution.
But there are a lot of problems with that.
Yeah, yeah. A lot of problems can be solved by very simple machine learning. Yeah, that's all I got.
Like an identity area bioinformatics, where we compare like really simple algorithms and statistical, like classical statistical based on neural networks, you can hardly find any difference. So there is no reason actually to use neural networks because they are really expensive, especially for startups to work with. So I would say just like stick to classical statistics.
Yeah, well, definitely. Okay,
Awesome. Thank you.
thank you.
Thank you.
All right, everyone. Thanks for joining us online for the meetup. We had a great crowd this month in person, so hope to see some of you who are local in person next time. And first Saturday of the month, so we'll have our next monthly meeting. And in the meantime, if you have any requests, let Ryan or me know on Slack. We're looking at some different options for additional content to talk about. All right. Take care, everyone.